Okay, let's see here. All right, yeah, it's time. So, does anyone have any questions that they want to bring up? Okay, so what did we do just in the last session? So what we did, we said that, we're asking kind of an abstract question. So we're saying, okay, look, I have this vector x naught. It's just a particular vector x naught, and I want to ask, if I put this through a matrix phi, will I be able to get it back by solving L1 minimization, right? And so, what we've been able to do is be able to write down a set of conditions that depend on the support of x naught and the sign of x naught on that support. And we derive these conditions by, looking at kind of duality theory, basically, looking at a derivative and setting it equal to 0 in some sense. And they sort of boiled it down to two questions. So one is like, if I look at, just the locations in phi, to pull out the columns of phi that correspond to the support of the signal, does it have full column range? And so that's the same as saying, is phi gamma transpose phi gamma invertible? And then sometimes, that we need that anyway, because like what that would say is like, if this weren't true, that would mean there were two signals on x naught. Two signals on gamma, such that phi times each of these signals was the same thing. It means I couldn't tell apart even two different signals on gamma. Much less that signal from every other signal. So we definitely need that, but of course we need to, this depends on, the matrix phi and the set gamma, so it needs to be checked. And the other thing we need is like, or we don't need, but another thing that's sufficient is if we, look at the pseudo-inverse of phi gamma and apply it to just the vector plus or minus 1s. That's the sign sequence of this vector we're looking at, asking if we can recover. Then I take phi transpose times that. Is that less than 1 everywhere off the support? Those are the two things you need to check. Okay, so let's give it a... What I want to do now is give you an example of how we get an actual result using these things. All right, this is nice. This is great. This, it maybe sheds a little light on it, but let's show how you actually use it, and that will actually maybe better help motivate, what went on in that first hour here. Okay, so here's what we're going to do. We're going to return back to our spikes and sign dictionary. And why are we going to do this? Because we put in a lot of effort yesterday in looking at this uncertainty principle for these things. And it's actually going to tell us a lot about, that uncertainty principle is going to tell us exactly this. And also play a role in whether or not this is true. And it's going to be very simple calculations given that uncertainty principle is true. So we're going to look at right now, for this particular moment, the particular case where phi is the n by 2n, little n by 2n matrix In. So identity for discrete Fourier transform. So now we can ask people, when we talked on Tuesday afternoon, we asked, okay, when is the sparsest decomposition unique? Right? That is, if one is sparse decomposition exists for f, and we said by sparse we mean less than square root of n terms. So I said if I have a way to write the vector y as a superposition of fewer than square root of n spikes and signs, then there's no other way I can write it with less than square root of n spikes and signs. There's only one way to write it as a vector that's sparse. Now what we're going to show is, okay, if I give you such a signal, and I actually want to figure out what the spikes and signs are, I can do that using L1 minimization with only slightly stronger condition. So let's look at what the condition is. So I say, okay, now, what I have here, let me just make sure. I have a, just not to change the notation too much, I have a x naught over here. I observe y equals phi x naught. So it's some superposition of spikes and signs. Then I ask, okay, when is x naught the unique solution to this phi x equals this L1 minimization program, right? And so what that's going to do, that's going to recover a coefficient vector out here, right? And what that coefficient vector will tell you, the top half will tell you where the spikes are, the bottom half will tell you what frequencies the sinusoids are at and what their complex amplitudes are. Okay, so and the point of returning back to this is we have these nice conditions, and we can use what we did yesterday to talk about when they're true in an intelligent way. Okay. I actually did call this thing alpha naught. This doesn't need this. That's fine. Okay, so what do we need? First thing we need is let's check if this matrix is invertible. So we went through a lot of stuff yesterday, and what we did when we were also arguing about when we were deriving this uncertainty principle, it also had to do with did this matrix have a null space, right? And since the matrix is symmetric, it's sort of exactly the same as saying is this part of the matrix invertible? Is this thing invertible? And so, what we did to show that is we said, okay, really, I can write this matrix as an identity plus this matrix G, right? And the whole idea was I could try to bound, how big this matrix G was, and if I could show that the operator norm of this matrix G was less than 1, then I would be assured that this matrix would be invertible, and hence, would not have a null space, right? And what we did to do that is we said, okay, actually the operator norm of G, we had this bound on it that it was less than or equal to the number of spikes we had times the number of sinusoids we had divided by n. Right? And that's where we came up with this uncertainty principle that, if t times omega is less than n, then, this works. So for us, like the gamma, I should write this down. Our gamma is the union of these two sets. It is T union omega. And then, of course, since they're disjoint, our size of this is T plus omega. Right, we also had this condition. So we can write this condition two ways. That the size, number of spikes times the number of signs was less than n, or the number of spikes plus the number of signs was less than 2 times the square root of it. Okay. So that's where we are. So here's what we can say. We can say, okay, look, let's just introduce this constant delta, and we'll fill in what delta is in a second. But we'll say, look, if we can establish that t times omega is less than delta times n, right? Then immediately I can say that the size of G is less than delta, right? And if the size of G is less than delta, that means that all the eigenvalues for this matrix are between 1 minus delta and 1 plus delta. Right? Which means that all the eigenvalues for the inverse of this matrix are between 1 over 1 plus delta and 1 over 1 minus delta. Right? So in particular, the operator norm of this is less than or equal to 1 over 1 minus delta. Okay. So, we know we can achieve like delta less than 1. We can make this all make sense, right? Have this denominator be well behaved when t times omega is less than n, right? And then we also saw that as being the same as the number of spikes, the size of the support of alpha naught, or in the language of this particular problem, the number of spikes plus the number of signs is less than 2 times the square root of n. Okay, so that's one condition. Less 2 times the square root of n, and that's nice because that's exactly the same condition under which the spikes and signs are identifiable. Okay, so that's that's good, and that basically came from the same calculations we did. So there's number 1 checked off. This is true if the size of the set is less than 2 times the square root of n. Okay, so now let's look at let's try to check this thing. Right, so let's construct this V. Since this exists, we have every right now to construct this V. We construct this lambda. I don't know why I called it lambda here. Maybe I should call it U, as I did in the notes. And then, we'll see what we can do is say, okay, look, this is invertible. Then we have, again, every right to write this. And we know that on the support, that it's going to be equal to the correct sign sequence. So all we need to do is check off the support, is this quantity less than 1? Okay, so what are we doing here? Basically, we're saying, okay, look, here's this quantity here's this quantity B, and then let's look at the entry at location gamma of U. So that's the same as taking the gamma column of phi and taking its transpose and applying it to U. Okay, so that's what we're doing. And again, if I look at that, what is that saying? That's basically like saying, okay, if I could treat this as a vector W gamma, what I'm really looking at this entry as is an inner product between this vector W gamma and the sign sequence Z naught. Right, so this only depends on the matrix phi and the index gamma, and of course the index set cap gamma, and this is the sign sequence of the vector. So I need this inner product to be less than 1. Okay. Right, and here's one of the vector, and the other vector is the sign sequence. So all we do for this, like if I want to bound the absolute value of an inner product, there's maybe lots of smart ways to do it, but one first thing that always pops to your mind is Cauchy-Schwarz. I can always bound the size of an inner product by looking at the product of their L2 norms. Okay, so let's just do that. So, we know that Z naught, the size of Z naught is, the number of spikes plus number of signs. That's the size of the support. So then if it's a plus or minus 1 vector, the L2 norm of that, so if I put, since Z contains just things that are plus or minus 1, if I square them and add them up, I just get the size of the support, and I take the square root of that. That's the term I see here. Okay, the norm of this other term, so this is matrix being applied to another vector, right? So I can separate that into the norm of that said vector times the operator norm of this matrix right here. Right, so all I do is very simple thing, break this up into 3 terms. Okay, so this vector, this is basically, so what goes in here, remember what this is. This is basically, a vector which just contains 1s or plus or minus square root of n, right? And same thing with this vector, it just contains 1s or plus or minus square root of n. So at the end of the day, so this contains only 1s or plus or minus square root of n, or some number that has magnitude 1 times square root of n. And so at the end of the day, what this vector does, this vector also has entries which are either equal to 0 or have a magnitude of 1 over square root of n. And not only that, we know exactly how many of these terms have magnitude 1 over square root of n. It's again just t plus number of spikes plus number of signs. So the 2 norm of this we can bound by square root of number of spikes plus number of signs divided by n. Right, in this guy, we have a bound for from what we did earlier. We said, okay, if we know if we take t times omega less than delta n, we know we can write this. So this is like this. Okay, so now the question is, when is this less than 1? Right, so I think if we just realize, so look, we need at least to make this is going to be greater than 1. Right, and we're going to get here like t plus omega over square root of n when I multiply these two. So at least I'm going to need t plus omega less than square root of n to have any hope. Right, so if I do that, that means I automatically have the product of the two things is less than n over 4. Just again because of the relationship between arithmetic and geometric mean. So what that means, if I have, if that induces this, that means I can, if I have this, that means I'm taking product of these two things less than a quarter times n. So this means I can plug in a quarter for delta. And what do I get? I get the size of the support I can have, the number of spikes plus the number of signs, is 3/4 times the square root of n. And then I can say that alpha now will be, in that case, the unique minimizer to 4. And so that's, that's neat. So it's neat for the following reason. What it's saying is, like before we were saying, look, this thing is only identifiable. Like there's no other sort of way. Where I'm only guaranteed this sparsity composition is unique, is if the number of spikes plus the number of signs is less than the square root of n. Right? That's if I want any hope for solving the general problem at all, I need this to be true. Right? This is kind of like when the L0 norm works. So what we're saying here is like, the L1 norm is guaranteed to work, just a little bit tighter condition. I just need the signal to be just a little sparser. And then L1 is guaranteed to work too. Okay, so again, like all of this followed from, what do we have? We had these nice, kind of, call them duality conditions for when is X naught a unique minimizer to the L1 program. And then we had this uncertainty principle that we derived for the spikes and sign dictionary, and we just used it a bunch of times. So we used it here, right? And we used it here to bound that thing. And then the rest of the stuff just followed from properties of these vectors. Right, so at the end of the day, it's all very simple if you talk about things in the right order. Okay, so that's one good example of results you can get simply by writing down sort of these sufficient conditions for being an L1 minimizer of an L1 program. So, you can extend it. I wrote here, maybe we won't go through this because, we've already spent some time on this. We won't go through this too much, but basically you can extend this to dictionaries of small coherence. So exactly the same thing. If I have, instead of spikes and signs, I take phi as, just the union of two orthobases, psi 1, psi 2. And now, I need some notion of these orthobases being different than one another. So I have this coherence parameter mu. And basically, you can push this whole argument through again. And you get this sort of nice condition that if the size of your support set is 1 over twice this coherence, then this stuff works. All right. And so remember that in the spike and sign case, this coherence was like 1 over square root of n. So we recover square root of n over 2 here. We've just lost a little more because we're doing things in general terms instead of 3/4. Okay, so that's a nice application of these duality conditions. So these, this idea, and again was used to do many things at the advent of compressed sensing. So there used to be how it would work. You would say, okay, look, I'm interested in all gammas of a certain size. And then you construct very careful bounds for what the sort of eigenvalues of phi gamma transpose phi gamma would look like, right, as a function of this size of this set, right? And you'd get something like, it has to be square root of the size of gamma over n. So you need n at least then for s times log n over n. So you need that. Then you need to check a condition like this, right? And the condition, the way you do it, you have to be it has to be a little nicer than just checking Cauchy-Schwarz. Again, you have to handle those bounds with a little more care, but the sort of roadmap is exactly the same as this. This is the kind of things that were done and actually are still done. Okay, so that's nice. So this is a nice little packet which derives from first principles. What does it mean to be the unique minimum of this problem? And you can see it's a nice, very beautiful combination of geometry, the way we sort of thought about, descent vectors and thought about as Lagrange multipliers as trying to be co-aligned with this gradient. And that's a combination of that with linear algebra, right? All these things we write here are in terms of linear algebra. So that's, really gets at kind of why, this sort of stuff is mathematically interesting. It's a combination of these two modes of thought, if you will. Okay, are there any questions about this particular way of doing things or these particular ideas? Okay, so that's good. Let's move on to something a little different. Okay, so now, forgive me, we're also going to look at again at a sufficient condition for, quote-unquote, L1 recovery. The condition will be much simpler and much more familiar in that it's going to be this quote-unquote restricted isometry property for this matrix phi. The result will be slightly harder to derive, but not really. And it uses sort of a very different technique. It doesn't use this idea of duality. It kind of directly uses geometrical ideas. And so in that sense, I don't know, maybe that's nice, maybe it's not. But the point is, here's kind of what we're after. So we're going to shift gears. What we're going to do is we're going to look at prove that there's another set of sufficient conditions. It's in some sense a stronger condition for X to be a unique minimizer. But the nice thing about this condition is it really only depends on the matrix phi. Right? And so what it's going to say is like, if I have a phi that obeys this property. So basically, what this says is like for any 2S sparse vector, it preserves its energy, more or less. And another way to think about this, another way you can write this is if I have any two S-sparse vectors, the distance between them is preserved through phi. It's the difference of a 2 S-sparse vectors is something like a 2S sparse vector. Okay, then what we'll be able to say is that you can say two things. So one thing we can say is that the solution to this program is exactly x naught, right? And how do you make an argument like this? Well, you say suppose not, right? Suppose that there's a x prime that's S sparse and phi x prime equals y. So suppose this is true, right? Then what does that mean? Well, basically it means that phi times x naught minus x prime, this equals 0, since phi x naught equals 0, and also phi x prime equals since phi x naught equals 0, and phi x naught equals y, and phi x prime equals y, right, supposition. So what does that mean? That means that the norm of this is equal to 0, obviously. For 0 vector, the norm is equal to 0. But what the problem with this is S sparse. This is S sparse. So this is less than or equal to 2S sparse. Right, so it can't be true expressly because we have this lower bound. So I mean, again, it's like I'm looking at saying this argument is much simpler, but it has this sort of exact theme of let me look in the null space and see if that's inconsistent with my geometric properties. We're here. The geometric property is I need this vector to be 2S sparse to kind of at least to less than or equal to 2S sparse to decrease the L0. Kind of like you look at a descent vector, and then you say, okay, this descent vector must also be in the null space. Those two things are incompatible with one another. So we'll do exactly the same for L1. And almost using this exact line of reasoning, it just takes longer because, you'll see why. Now, you can say exactly the same thing for 2S ring. We're going to do something a little weaker. We're going to do 3 S-sparse vectors instead of 2 S-sparse vectors. The reason is it just makes the argument much simpler, right? And I think if you appreciate what goes on here, you'll certainly be able to appreciate how to do the extension. So here's exactly what I want to argue. Right? I want to argue that if you have an n by n matrix, so forget about the matrix being random, or forget about everything about where it came from. It's just an n by n matrix, and it has this property that if I look at any 3S sparse vector, the energy is approximately preserved. So I can get delta 3S and delta 3S here. Then, if I observe this vector through phi, so I observe y equals phi x naught, then I can recover x naught, by solving this optimization program. Namely, if I plug that same y in here as a set of constraints, the solution to this is exactly x naught, and that's the only solution you can have to this. Okay, so the way we're going to do this is, again, different than constructing this dual certificate like we did in the last lecture. It uses, in some sense, you start off just, again, with these sort of direct geometrical properties. You just have to manipulate them a little more subtly. Okay, so here's what we do. Let me draw on the board all the sort of relevant quantities here so we can keep on. Okay, so we're going to call the solution, so x sharp is the solution to this, and h is the difference between x sharp and x naught. So essentially what we're saying is, So if we have something like this, maybe this is our vector x naught, this is our vector x sharp, right? And what we're saying is that like maybe h is the difference in between these two. There's one key problem with this, and that's one did not go through. Sorry. So here's x naught. Here's your solution x sharp, and h is the difference between those two. Okay, so basically, what we're saying is, the first thing you say is like if h is the difference between, the true solution to this, whatever it is, and x naught, and I want the answer to be x naught, I'd like for h to be 0, right? So that's kind of what I'm trying to show, that h is identically equal to 0. Or find conditions under which h is guaranteed to be exactly 0. Okay, so we know two things. There are two things that are true, and we'll show that these two things are, again, the point is showing that these two things are just at complete odds with one another, unless h is exactly equal to 0. Here are the two things. The first thing is that, any such h, that's the difference between the signal you're after, the vector you're after, and the true solution, it has to be in the null space. Right? Because they're both feasible points. If I'm saying I really did observe y equals phi x naught, and x sharp is the solution to this, meaning x sharp must be feasible, then phi x sharp and phi x naught, they have to be the same thing. They're both equal to 1. So any h, this h vector is in the null space. Okay. Second thing we know about h is that when I add it to x naught, it has to decrease the L1. Right? Why is that true? It's just true by definition. It's saying like, look, x sharp is the smallest L1. Basically what it's saying x naught plus h, this is just x sharp. And if I'm calling x sharp the solution to this program, well then it better have L1 norm less than or equal to x naught. That's just, by definition, x naught is also feasible. Okay, so what are we going to say? We say, okay, look, if this matrix has this 3s grip property, then these conditions are just absolutely incompatible with one another, unless h equals 0. So it's really almost the same as in the sort of L0 case. Just it's just going to require a little more manipulation. Okay, so that's what we do. Show these two properties are incompatible with one another. So this is sort of the picture I've been drawing on the board. It's like if you can always think about these things, and this sort of set of line of argumentation in particular is if I'm sitting at x naught and I draw my null space, down there through x naught, so moving along this line, this is the feasible set, so moving along this line, I'm adding vectors in the null space to x naught. So if I'm saying, what this picture says is, okay, descent vectors, things that decrease the L1 norm, they move from x naught into the interior of this L1 norm. So in this case, none of those can lie in the null space, so it's fine. So basically that means these two things are incompatible with one another. Every h I can add to x naught that decreases the L1 norm is not in the null space. Likewise, everything in the null space does not decrease the L1 norm. And then here's failure, right? So when this thing slices through the L1 ball at x naught, it means I can move along this null space and decrease the L1 norm. Okay, so that's the kind of geometrical properties or the geometrical picture to have in your mind as we go forward. Okay, here's the first fact, right? So again, it's like what did we say before had to be true in this? So in the L0 case, we said like, well, what happens is if we have these two S-sparse vectors, and we subtract one from the other, the result is 2 S-sparse. And that was kind of like our geometrical property, and that was immediately, violated this restricted isometry property. So we do something similar here, although we can't say anything immediately. It takes us, 7 or 8 slides, but it's okay. So what we can say is like, look, this is actually a property we're going to have for any descent vector h. So for any vector which lowers the L1 norm of x, you have the property that the sum of the magnitudes off the support of x is less than the sum of the magnitudes on the support. Right? So in some sense, what's that saying? You can kind of see that here. What it says in R2 is it means, the direction of h, it has to have more verticalness in it than it has horizontalness in this case. So this is, since x naught is supported on this vertical axis, h has to be more aligned with the vertical axis than the horizontal axis. In general, if I sum up the magnitudes on the support and sum up the magnitudes off the support, h has to be, the sum of magnitudes has to be bigger on the support. And it's actually, you can do this pretty quickly. So you say, okay, look, I know since h is a descent vector, I know that this must be true. All you need to do is just this is called the quote-unquote reverse triangle inequality. I just separate h into things that are on the support and parts that are off the support. Those are disjoint sets. So then I can just say immediately, okay, this norm of the sum of two vectors is greater than the difference between their norms. Again, kind of like the reverse triangle inequality. And what that says, since these two things are disjoint, so x naught is supported only on gamma naught. And by definition, h gamma naught complement is supported on the complement of gamma naught. So, since those two vectors are disjoint, and I look at their L1 norm, I can just separate it into the sum of their L1 norms. This is just simply because these two vectors have disjoint support. So this is what we get. And that's exactly the content here. So, remove the x1 from both sides is saying the difference between these two things is less than 0, which is exactly it. Right? And that's just a generalization of the fact that this guy has to be more aligned, this way than he is like that, just because I won't have to cut into the cone. It's like, this is a purely geometric thing. I'm like coming off this point of this L1 ball, and it's just I'm very constrained in how I move. And that's the algebraic description of what that constraint is. Okay, so that's one thing right? Every vector that's a descent vector has to have this, and so it's kind of like, now we just want to show this is incompatible with being in the null space. So this is what we say. We say, like, look, okay, this has to be true just for properties of the L1 norm. But if it's also true that this matrix has the quote-unquote 3s grip, and h is in the null space, right, then this can't be true. In other words, there's some rho less than 1, such that the sum of the magnitudes on the support is less than rho times the sum of magnitudes off the support. So in some sense, this is saying, like, if h is in the null space of this matrix phi, with the kind of the flavor of what we'll say here, then h has to be kind of spread out. It can't be too concentrated on the support, right? Not too much of it can be concentrated on the support phi now. Right, so that's kind of what we're going to show. So this first half we showed. Now we just need to show this. We show for any vector that's in the null space, the sum of the magnitudes on the support of gamma naught is less than rho times the sum of the magnitudes elsewhere. So like nothing here, let's just pause for a second. Nothing here really depends on x except for this, the fact that we have the support. Right? And the support, as we'll see, it really just depends on the size of this thing. This is where this restricted isometry property comes in. Okay, so let's look at this a little closer. What's the implication of h being in the null space of phi with respect to this restricted isometry property? So, real quick, just because I apply these once and twice, just our memory. If I have a vector which has only s components, so for any vector, I can always bound the 2 norm of that vector by its 1 norm. And I can always bound the infinity norm by the 2 norm. That's always true. It's also true I can reverse these if I put in inequalities. So the 1 norm is always less than square root of number of active terms times the 2 norm. The 2 norm is always less than square root of number of active terms times the infinity norm. Right? So this is true, and then I can go backwards by putting in square root number of non-zero terms. Just keep that in mind as we go forward. Okay. So here's what we do. So I fix any vector h, and the only thing I'll say about h is that it's in the null space of So you give me any vector h that's in the null space of. And then here's what we do. So we say, okay, here's gamma naught. This is the support of x naught. So h is whatever, it's arbitrary. It can be anything. And then, it has, so it's just wherever, there's a bunch of different ones. H is arbitrary vector, so we say, okay, what we do is we'll divvy up, we call gamma naught the support of x naught. And then we say gamma 1, this is the locations in H. Again, H is fixed, so some fixed but arbitrary vector in the null space of the 2s largest terms, again, of H in gamma naught C. Right? And then phi 2 is the locations of the next 2s terms. Right? So the idea is like, okay, what we're going to say, as you might be able to start guessing by now, is like, look, if I divide this up, what this means, it means that, if I look at this, no matter what H is, if I look at it restricted to each of these sets, that phi has to preserve its energy on the sets. If I say phi has this restricted isometry problem. Right? It also has to preserve it on the union of gamma 0 and gamma 1. So that's basically how this is going. So H is just some vector in the null space, and all we do is reorder it from biggest to smallest and label it like this. Okay, so what's one easy thing we can say? So we say, okay, look, we know that phi H is equal to 0, so it's equal to 0. And then we know that these supports, these different gamma j, they're disjoint from one another. So we can just rewrite H as the sum over all these different supports. And then we just break this into two parts. So basically we say that we look at H on the support of x naught and its other 2s biggest terms. Right? So we have this 3s sparse vector here. And then we have a sum of phi applied to a bunch of other 2s sparse vectors. Right? And so again, what we want to show now is, when we do this, it suggests that this quantity sort of has to be, because H is spread out, this quantity we're kind of going to show has to be sort of much smaller than the magnitude of the quantity on the left. Okay, so that's just, this just follows from H being in the null space and our definitions. Okay, this is just triangle inequality. So I told you we do triangle equality a bunch of times. Just pull the norm inside the sum. This is greater than or equal to because that's there's a negative sign there. And now, we know what to do. Like, what do? We have phi applied to a 3s sparse vector, phi applied to an s sparse vector. So we just apply this rip. Okay, right. So since this is equal to 0, we know that basically the 2 norm of H on the gamma 0 union with this locations big S terms, that has to be less than the sum of the phi applied to the norm volume. Right, so then this is where we apply the rip. So we just apply it to the left. So this is, of course, each of these. This is each of 2s sparse vector. So here comes the rip, and we turn that into norm of H. It's kind of like, here we're saying something about the norm of phi times H. We get rid of the phi's and just talk about the H's. And then we know this part is greater than, since this is a 2r sparse vector, we know we have this lower bound from this 3s rip. This is a 3s sparse vector. We have this lower bound like this. Right, so now what we can do is we can relate the 2 norm, like on this kind of augmented support of H, to the sum of the 2 norms outside of this augmented support. So just collect these two things. So this is what we have. Okay, so in some sense, what are we doing here? We're trying to show, again, these are 2 norms, and we want to get it back to L1 norms at some point. But basically, we're trying to show that the size of H, like near kind of on gamma naught, it has to be small. In some sense. So now we just have to manipulate this thing until it gives us what we want. So here's what you do. You say, okay, look, first thing I can do is replace what's inside here by an infinity norm. All right, so I can just, by these properties of the relationship between L2 and L infinity norm, since each of those is 2s sparse. And then the next thing I can realize is that, okay, look, the maximum. So here's the kind of the trick we have. So we've defined everything in gamma 3 is smaller than everything in gamma 2. Right? Everything in gamma 2 is smaller than everything in gamma 1, just because of the way we define these sets, right? So that's just how they're ordered. So what we can say is like, look, the biggest term in gamma 2 is less than the average of the terms in gamma 1, since everything in gamma 2 is less than everything in gamma 1. So all you say is, I can write the average of the terms, or the magnitude of the terms as 1 over s. So I can replace this with the sum from j greater than 2 to j greater than 1. Replace this by 1 over s times the L1 norm. So it's like the average of what came before. And you get something like that. So we get L1 norm on the right. We're starting to get at it, and we can just manipulate that. So that's what we have. All right, so now we can say, like, okay, look, the L2 norm of this is less than or equal to the L1 norm off the support divided by the square root of s times some constant, which just depends on these isometry constants. So then we can start to manipulate this thing on the left, right? And so what we can say is like, okay, gamma 9 and gamma 1 are disjoint. So this has to be bigger than this guy. All right? Again, what we want to do is get some kind of L1 norm over here. But we know how to do that, so we can simply replace that. We can sort of bound the L1 norm by square root of s times the 2 norm. So we get something like that. And so this is kind of exactly the form we want. We have, the L1 norm on the support of h is going to be bounded by some constant times the L1 norm off the support. And that gives you the result. Right? And so that basically you can show that simply as a consequence of two things. H being in the null space of phi, and phi having this restricted isometry property, just sort of, preserving the norm of vectors which were 3 S-sparse or less, gives you this result. So all you need for this to be strictly less than this is for this rho to be less than 1. So if you have an isometry constant which is less than a third, you can show that this constant is less than 1. So that's, what we would call complete success. So there we have it, right? So again, what we can show is like, if, this gamma is an approximate isometry of 3 S-sparse vectors, and I observe such an S-sparse vector through phi, then it has to be the unique solution to fit. And the way we did that, again, is very geometrical. It basically said that, you need... for any vector h which lowers the L1 norm, so for any vector h which also lowers the L1 norm, that's incompatible with it being in the null space if phi has this restricted isometry property. So, in some sense, it's almost like we wrote the short L0 proof on the board. It's almost the same thing. We just had to be a little more careful when we went through these 5 or 6 slides here. But other than that, the rhythm was exactly the same. It's like you have some geometrical condition on your descent vectors h. You know that h must be in the null space, and you show that this sort of restricted isometry property is a direct opposite of this geometrical condition. Okay, so let's stop there. Why don't we? And then let's pick it up again at about 4 o'clock. Right? And what we'll do then is we'll talk a little bit about stable recovery, how we can sort of modify things to show that the L1 recovery is stable. Okay, we'll talk then.